So I think we can get started. So Howard, you could please introduce yourself, but I'll just say, as a precursor, I met with Howard some time ago at NIST, found out about his requirements. These are a little bit different from what we normally do, but it seemed like an interesting thing to try out, and so I'll let Howard take it from there.
Okay, good. Well, hello everyone. It's nice to be here. This is my first time giving a talk like this on a computer, so I hope you'll bear with me. Yeah, my name is Howard Cohl, and I have I've been in academia I've had a various career doing lots of different things. I started out interested in astrophysics, and then I got a PhD in astrophysics doing massively parallel computing of astrophysical systems. I did my PhD at LSU, and I did my undergraduate degree at Indiana University, and I also worked at the National Solar Observatory in Sunset, Mexico for 2 years. And after I got my PhD in mathematics, I worked at the Naval Oceanographic Major Shared Resource Center, which is a big supercomputing center in Mississippi. It's then a spaceflight center for the Navy. And then I did a postdoc at the Lawrence Livermore National Laboratory, working on also astrophysical systems. And then I did a postdoc at the University of Exeter in the United Kingdom, also in astrophysics. But I decided at that point I really wanted to follow my interest in mathematics. So then I went to New Zealand, and I got a PhD in mathematics at the University of Auckland, and I've been doing mathematics ever since. But since I came here to NIST, I got interested in a computer science project, which I'm going to talk about today. So maybe this is a good place I can start my talk.
Howard, can you please make it a full screen, the PDF?
Oh, no, but then I won't be able to see if anybody chats me. But if that's okay, just let me know if that's the case. Okay?
Sure, yeah. We'll alert you, if anyone, we'll be watching the chat, and we'll alert you.
Okay, that's fine. So then, all right, you all can see it now, huh? So the title of my talk is XSEDE and the NIST Digital Repository of Mathematical Formulae. The people who are working on the project at the moment, and some past and present, in particular at NIST, is me, and then we're all in the mathematical software group. Me, Marge McLean, and Benita Saunders. They originally are working on the Digital Library of Mathematical Functions project, and they got interested in my project when I proposed it to them. So they've been on the team since it started in April of 2013. And since then, we've brought on board Moritz Schubatz, who's at TU Berlin in Germany. And I had a variety of high school students who've worked on the problem. And I've also had an undergraduate student from Virginia State University, and we had a joint publication together at the conferences in Intelligent Computer Mathematics. It was recently held in Portugal, in Coimbra. And I presented this material there, and it was well received. So that was good. And then I had these high school students who I've worked with. This summer, I had Alex Danoff, Jimmy Lee from local high schools, and they've done really great work. I've been really proud of them. And last year I had high school students who were here over the course of the year, Jake Migdal, Amber Liu, and Cherry Zoe. Cherry is actually still working with us. I'll talk more about the work she's doing, and I currently have 2 more high school students who are working with me during the course of the year. So I've had really great success with these students in my mathematics projects as well as this computer science project, so I'm really proud of that. So what am I talking about today? I'm talking about, we're calling it the Digital Repository of Mathematical Formulae, and what it is it's actually still in development, so it's not complete yet. But what it's meant to be is an online compendium of mathematical formulae, in particular for orthogonal polynomial and special functions. Orthogonal polynomials and special functions such as Legendre polynomials, Hermite polynomials, or more general special functions such as gamma functions, Legendre functions, hypergeometric functions and so forth and so on. That's my area of interest in mathematics, is in particular special functions and orthogonal polynomials. And NIST has a really strong background in this area, going back, since before World War II. They've been developing numerical tables for special functions, and they're really important in doing simulations or massively parallel simulations. They really are the building blocks of numerical algorithms in many cases. So that's sort of the goal of this, is that we have some analytical representation of some formula, and currently they exist in books, and there are some locations on the internet where you can find these formulas, but no sort of centralized database where you can get information about them, in particular, which satisfies certain requirements and goals that I'll talk about in a little while. So what we're trying to do is using Web 2.0 technologies to sort of interact with these formula. Instead of being a static presentation, we want to develop a platform which encourages community interaction and collaboration. So one of the key features of the DRMF is the utilization of these macros, which are used in this other project, which I mentioned Benita and Marge were involved with, called the Digital Library of Mathematical Functions. The DLMF you can find online. I could probably this is such an important thing, I think maybe I will just show you really quick just what it looks like. If you go to dlmf.nist.gov, I'm also working on this project as well. And, it's called the NIST Digital Library of Mathematical Functions, and there's a book that corresponds to it called the NIST Handbook of Mathematical Functions. It's the follow-up of a very famous book on special functions called, which was edited by Milton Abramowitz and Irene Stegan, and the final version was in 1972 with all the errors fleshed out, and this is the follow-up of that. This was published in 2010, and you can see all the basic special functions that you would, pretty much all of them, that you're interested in, well, with a few exceptions, are listed here, and is actively maintained, and has all kinds of nice features. So I can go back to that sometime and talk to you more about that. But right now I'm focusing on it's an offshoot project of the DLMF, and the DLMF maintains these macros, they're LaTeX macros, for the different special functions and orthogonal polynomials and other mathematical objects that are used in the Digital Library of Mathematical Functions. And some of the nice things about them is that they tie these specific character sequence to well-defined mathematical objects. Also, we've generated a glossary which allows us to link from the macros themselves to definitions for the objects, and we link to the Digital Library of Mathematical Functions or the Digital Repository of Mathematical Formulae if, for instance, that definition is not given or is not well explained in the DLMF. Now, the way we actually are generating the software is we're using the MediaWiki, which is the wiki software used by Wikipedia. And in particular, some aspects of it that we take advantage of are the math extension for MediaWiki. So MediaWiki is the software written in PHP. It's a very large software, and there's extensions to that software which have been developed, which are used in Wikipedia. One of them is the math extension, which we rely heavily upon. Moritz Schubatz, who's next to me, is the main developer for the math extension, so we're really, really glad to have him on board. Our work in the DRMF is we really hope that the things that we learn and we're trying to accomplish for the DRMF will ultimately migrate, and I think already it's happened in several instances, into the math extension to make the math extension even better for all of Wikipedia. So one nice thing that the math extension currently has, which is being tested in beta mode at the moment, is the MathML support. So currently, or on the production server for Wikipedia, mathematics is displayed as, I think, PNG images. With MathML, you can actually display mathematics in a nicer way. And the HTML, which is generated, which is XML and MathML, which actually gives more semantic information about the mathematics that you would like. And another thing that's used is LaTeX ML, which is a software which was developed here at NIST, which starts from LaTeX and generates MathML. And I'll talk more about that in a little while. And also another nice thing that the Math extension has is MathJax, which was developed by the American Mathematical Society, which I'm a member. It uses, it's very nice. It's a nice way of displaying mathematics if, for instance, your browser is not MathML compatible. And actually, a lot of browsers are not MathML or XML compatible, such as Windows Explorer, for instance. But Firefox, for instance, is. So our primary tool for displaying mathematics using MathML is the Firefox browser, but the Chrome actually works as well. But each browser is in its own state of development for MathML, and maybe Moritz can talk about that a little bit later. So what we've got at XSEDE, for instance, are demo, development, and server instances that the XSEDE helped us develop these instances, which we're actually using to develop and demo our this DRMF MediaWiki implementation. Also, we're developing at the Wikimedia Foundation. It's actually called Wikitext. It's a server in San Francisco, which Wikipedia and the Wikimedia Foundation use to develop extensions and offshoots of Wikipedia. Exactly. So we're very happy to be doing there, and they have actually a nice production environment and debugging environment that we rely on heavily. Which we don't currently have that implemented on the XSEDE on our XSEDE instances, but we've been in discussion with the team there to try to get it installed as well. So the DRMF has certain goals, and I'd like to sort of summarize them if I can. In particular, it's designed for a mathematically literate audience. It's not aimed at a lay person at all, but what it should do is facilitate interaction among a community of mathematicians and scientists interested in compendium of formula for orthogonal polynomials and special functions. Secondly, it should be expandable. It should grow, be able to grow, allowing for input of new formulae from the literature. Also, it will represent context. This is our goal, to represent the context-free full semantic information concerning the individual formulas. So they should be standalone, that you should be able to find all the semantic information you need by looking at a formula homepage, for instance, which is designed to give you all that information. It should also have a user-friendly, consistent, and hyperlinkable viewpoint and authoring perspective. The mathematics inside the DRMF should be easily searchable. And in particular, the mathematics, that's one of the main goals, is that if you want to search for a certain formula for a certain function, that you should be able to do that with the DRMF. And also, it should take advantage of modern MathML tools for easy-to-read and scalably rendered content-driven mathematics. So these are our main goals for the DRMF. And this project has been developing in several stages and in sort of different directions. There's many different directions it's headed. So I thought I would summarize a little bit about how that works. One of the first projects we have are to sort of, well, we would like to try to fill the DRMF with content which is available to us. Now, the first content which has been made available to us is actually the information from the DLMF, the Digital Library of Mathematical Functions here at NIST. The editors at the DLMF have given us permission to use the data and the source from the Digital Library of Mathematical Functions. It's actually given in LaTeX. Bruce Miller has developed here at NIST a software which I already referred to called LaTeX ML, which will start from LaTeX, and it will also, of course, LaTeX, we can easily generate a PDF, which is how the book was printed, the NIST Handbook of Mathematical Functions. But LaTeX ML will also start with LaTeX and generate a web page. And that's, so they both start from that same LaTeX source. So the LaTeX source is the origination of the content from the Digital Library of Mathematical Functions. And inside that source, Bruce Miller has developed macros for the orthogonal polynomials and special functions and other mathematical objects, as I already mentioned. And they're fully implemented in the source, in the LaTeX source. So the nice thing about these macros is that they contain all the semantic information about the special functions. So for the DLMF source, we already have those macros implemented. But for other sources that we might be interested in expanding the digital repository of mathematical functions to include, these macros are not implemented. There might be some macros which have been implemented, but certainly not the DLMF macros. And what we'd like to do as a standard is to use these macros to standardize our ability to search within our database. So we've also been given copyright permission to use source, the LaTeX source, from a really famous book on orthogonal polynomials written by Cook, Lesky, and Suarto. That's the KLS. And also there's an addendum which was written by a really great mathematician named Tom Kornwinder in the Netherlands, which gives some corrections and additions to the book. So I had students working on this project starting in December of last year, and they've been writing programs to convert the mathematics as it appears in the LaTeX source to implement the LaTeX macros. And ultimately, we've iterated to a solution which uses Python, which works very well, and it almost has completely replaced all the macros in KLS and the addendum written by Tom Kornwinder. Ultimately, that's the first step in building the repository. Excuse me. And in the next thing that you would need to do is to convert it into Wikitext. And for one chapter of the Digital Library of Mathematical Functions, I've actually written a program which will generate the Wikitext. There's other things that you have to do. You have to get rid of stuff that you're not interested in, such as graphics. For us, we're only interested in formulas. So, and other stuff that's in the DLMF or any of these other references that don't concern us. We're particularly interested in the formulas alone and any metadata associated with those formulas, which will help people understand those formulas. We've also been in contact with other authors for famous special function books, such as Andrews, Askey and Roy, Dick Askey. Andrews was a president of the American Mathematical Society, wrote an amazing book on special functions, and Murad Ismail, who we're in contact with for orthogonal polynomials. We've also been in touch with Mathematica. We recently, at the conference, we met Eric Weisstein, who works at Wolfram, and he's actually sent us information, or actually the data for their recent ECF project, which has the goal to catalog all known information about continued fractions. So we actually have that data, and what we'd like to do is incorporate that into the DRMF. So that's actually one of our long-term goals, is to be able to start with various sources, such as Mathematica source, and then generate media Wikitext that we can use in our DRMF project. We're even more ambitious than that. We would actually like to go one step back in case we don't have any LaTeX source for a book. We could, for instance, and I've been in communication with Alan Sexton, who's in Birmingham, who's developing very sophisticated mathematical optical character recognition software to actually process scanned images of a book where the LaTeX source, for instance, doesn't exist. There's a famous series of books on special functions called the Bateman Manuscript Project. There's actually 7 books, 3 of them, actually 5 books. 3 on higher transcendental functions and another 2 on tables of integral transforms. And we've gotten copyright permission also from the California Institute of Technology to use those manuscripts, and they're sending us books, and Alan is developing his software, which will then hopefully scan these books and generate LaTeX source. And once we have the LaTeX source, then we'll convert the special functions themselves, implement them into LaTeX macros, our macros, and then hopefully we can generate our Wikitext and we can incorporate this material into the DRMF. Also, there's other famous books, such as Bird and Friedman's Handbook of Elliptic Integrals for Engineers and Scientists. We would like to incorporate these books because it's a great wealth of information on elliptic integrals. And ultimately, what we need to do is then generate the Wikitext. And for instance, the only thing we've actually succeeded in doing that with is the DLMF. We've actually done one chapter, and I have some students working with me. We're trying to extend this to other chapters. And in the near future, we would like to generate the Wikitext for the KLS books and the KLS addendum. So that's one stage of our development. And for the Zeta and related functions chapter in the Digital Library of Mathematical Functions, we have a full implementation, which is stored on the XSEDE servers, which you can find there, for instance. And this is just a display of what the page looks like. It's actually a very long page. It contains all the formulas in the NIST chapter on Zeta functions. And you can see at the very top of the page, there's a linkable table of contents for the page. So you can click on these links, and they'll take you to the various parts of the page where these table of contents link to. And then you have a collection of formulas, like I've listed here, for instance, reflection formulas for the Riemann zeta function, and they're given here. Also, there's information such as constraints that the formula must satisfy, and also any substitutions which are necessary to understand the formula. So that's just an example. I can actually show you. In fact, maybe I will. I'll just show you really quick. I've got some pages loaded. This is actually on the XSEDE server right now. This is an instance called GW32, and you have basically this table of contents. So you can click on the table of contents, for instance, integer arguments, and then you have all these formulas for the zeta function with integer arguments. For instance, zeta of 0 is -1/2, and zeta of 2 is pi squared over 6. So this is in this instance, you can click on the formula itself. So the formulas themselves are the main focus of study. So you would then click on a formula, and it will take you to a formula homepage. And on that formula homepage, you have the formula itself, and then also a section for proofs, a symbols list. So you can click on the symbol itself, and it will take you to its definition, which is the same as this URL. So for instance, for the Riemann zeta function, it takes you to a link in the Digital Library of Mathematical Functions, which defines what the Riemann zeta function is, and there you can learn about the Riemann zeta function. So the DRMF is not a place to learn about functions. It's really a place to learn about formulas. If you want to learn about a function, you want to go back to the Digital Library of Mathematical Functions, which is a validated, time-tested, for 10 years they were validating this. So it's a really great, trustworthy source of information about functions. So we don't want to redo that. We're not interested in doing that. We want to take advantage of the excellent tool, which is the DLMF, and we link directly to it whenever possible. And then we also link to a bibliography. That's another requirement that the DRMF has, is that every formula must link to a bibliography. And in this case, the bibliography is actually online. So you can click on the link, and it actually takes you to the formula in the Digital Library of Mathematical Functions. Otherwise, in some cases where we refer to references which are not online, then our bibliography would refer to the book. So in that case, you click on the bibliography, and you can see, at the moment, we only have 2 entries. One is the DLMF, and the other one is a book on mathematical constants. And then if there's any URL links that we need, we would list. You could link them here, or you could actually go back to the formula in the Zeta and related functions page, or you can scan through formulas by clicking on these headers at the top and the bottom of the page. So for instance, here's Zeta of 4 and then Zeta of 6, and you keep going through the formulas, you can scan through them. So we modeled this after the Digital Library of Mathematical Functions. See, for instance, here's a formula which gives you the zeta function with 2n, where n is an integer, 1, 2, 3, etc., greater than or equal to 1. And it tells you that this zeta is the Riemann zeta function. You know, it tells you what pi is. If you want to find out what pi is, you can go to the DLMF. And then these b's are the Bernoulli polynomials. And if you want to know what those are, again, you can go to the link in the DLMF, and it'll tell you what they are. Okay, I guess I'll continue with my talk. So now I'll talk to you more about the macros, which are really the key to allowing searchability and adding semantic information. So at the moment, there's about 546 semantic macros, which were developed by Bruce Miller for the DLMF, and we've added an additional 49 macros, which we've generated by processing the KLS data. So they represent various objects such as sums, integrals, derivatives, other types of derivatives such as a Q derivative. We encapsulate semantic information such as various mathematical constants, such as E, I, pi, or the Euler constant. And the way they're built is that there's some mathematical function which is rendered here, and you've got a macro which tells you specifically what it is. And then for each macro, there's a link to a web page which gives you the definition. So I wrote just some examples of this is the macro for how you would actually write the macro for the gamma function, the Bessel function of the first kind, the associated Legendre function of the second kind, and a Jacobi polynomial. So then you have these formula homepages. So for instance, Wikipedia, the web authoring tools, they manifest notions or descriptions as first-class objects. The DRMF, as an encyclopedia would do, the DRMF does that with mathematical formulae. And as I've mentioned, in the formula homepages, we give a rendered description of the formula, any constraints the formula must satisfy, any substitutions which are required to understand the formula, the bibliographic citation for the formula. There's an open section for proofs. We're going to encourage people to enter proofs. There will always be a symbol list and links to definitions for the symbols, an open section for notes, and an open section for external links. Here's a sample formula homepage. I already showed you one. So for this complicated formula here, in order to understand that, there's some substitutions, some constraints. The proof at this moment is empty. No one's entered a proof for it. We do have some examples of formulas with proofs that we've extracted from the DLMF. So there are some proofs in the DLMF, and we've managed to build them into the DRMF. In fact, I'll just show you really quickly what this looks like, what the proofs look like. So for instance, if we go back to the home page, these pages have proofs. So this is an example of a formula with a proof. In fact, I think I have another here. So here's the proof. It says argue as in this formula. Go to this formula. So if you click on this formula, then it'll take you to the formula homepage of that formula. And now you're in that formula, and you see here for this formula, which is what was referred to, you have some constraints, such as the real part of s is greater than -1 and s is not equal to 1. And then we ask users to provide references to proofs, and then this is the proof itself. So you can see the formulas themselves are also clickable whenever they're available. So here's the definition. Here's an integral for the Riemann Zeta function, an integral representation. Yeah. And here's a formula for the gamma function.
Yeah, it's okay. It's online.
Okay. So you can, for instance, click on this formula for the gamma function, and you go to the page on the gamma function, and you can learn all about that integral for the gamma function. Right, so everything's consistently hyperlinked. So let me continue. So some questions that come to mind is, so how does one facilitate an effective community with interaction and contribution with such a resource? So we also want to ensure a high degree of computer verification of, if we can, to implement that for community if people are going to input data. And we'd also like to degree a certain significant amount of moderation. We don't want just anybody to enter data into it. We only want people who are going to give data which will help the library grow. And in general, you'd like to ask this sort of general question: how does one build a piece of intelligent software which is able to, scan in books, produce latex source, replace commands for functions in the source with these semantic macros? You would like to be able to extract data from the text, such as constraint data, which is not necessarily contained in the formula itself. Sometimes you'll mention that exterior to the formula. So that's some information which is relevant for the formula itself. So you would like to make it so that it's contained within the formula, and then associate any data with relevant formulae then we remove the text, produce the relevant Wikitext, and then upload that Wikitext to a publicly accessible server. And then ultimately, we'd like to be able to search that resulting mathematical database. How do you do these kind of things? So these are the kind of questions that we're really thinking about, and we'd like to answer.
Howard, this is Nancy. What do you mean by computer verification on the last slide?
Well, at a sort of a root level, we might like to do some just order 0 verifications, maybe some numerical tests. If you can get the computer output the formula in a format that the computer can understand, and then such as a Mathematica format, and then run some simple numerical tests with some ranges of variables that satisfy the constraints to see if the formula satisfies it. Another way to do that could be to actually generate a computer-generated proof of the formula. We've talked with some people who actually have accomplished some of that, and that's sort of a long-term goal as well, as trying to implement computer verification for proofs as well. Does that?
Great. Yeah, that answers it. Thank you very much.
Sure. Okay, good.
Yeah, this is Marla. It's very interesting. I think I was also wondering if the software stack that you're in on the previous slide that you're envisioning. I think go back to slide 9. Yeah, the intelligent software.
Oh yes.
What would you say is the state of all that, and then also lots of these things like MediaWiki are good open source projects, but also I wonder what the state of some of the scanning software is, if that's openly available. Do you foresee like an open, like say a GitHub-based community around all of these parts of your software stack?
Absolutely. That is a long-term goal of the project. Now, scanning, that kind of software is readily available. For instance, but one issue, for instance, is taking advantage or making care that you've taken into account the curvature of the book. Like there's lots of scanning software for doing that. Alan Sexton, he's actually had quite a bit of success in implementing doing scanning with just cheap scanners, which actually give something which is very reliable. In terms of generating LaTeX source from the scans, there is some software out there which will do that. It's called Infinity Reader. It's pretty good, but it doesn't always work, and we've actually found several instances in which it gives ridiculous output. So Alan's developing, for the next 2 years, he's developing, it's a research project of his, he's a computer scientist in England, and he's going to dedicate, he understands all the techniques which are used by Infinity Reader, and he's going to develop his own open source software to do this mathematical optical character recognition. So we have a lot of high hopes for this, and we think it's really, this is achievable in the next couple of years. And like I said, yes, this is something we would like to make freely available to the entire community, anyone who might be interested in doing this.
And based on following up with Nancy's question, I just comment that it is interesting that I never thought about it, but you can close the loop here on going from scanning text to to actually doing computer-driven verifications of the scanned text. So I know in general in digital humanities that's sort of the problem when you're just talking about free English text or something like that. That a lot of what's auto-generated is not very reliable.
Yeah, we understand we're not there yet, but we're excited about where it's going. One of the key challenges in doing that is, well, it's being able to process this stuff and then output it in a form that a computer will understand. And actually, I'm going to finish up my talk to discuss more about that. You really want to get it in a form that a computer can understand, and that's a non-trivial exercise in and among itself. Maybe I'll continue, because this actually connects nicely with that. So these macro replacements from well-constructed LaTeX source, the students are working on that. We've had really good success. It is also a very challenging problem because LaTeX is a universal Turing machine. You could have obfuscated LaTeX, and for stuff like that, if it's something really is crazy, we don't have much hope of being able to process it. But if we assume, which is not always a good assumption, that we can actually generate good LaTeX, we can actually process the macros as well as we can and handle special situations manually, perhaps. You just have to see how far we go. So far, we've had good luck, but we could envision in the future we might run into problems with that. We'd like to generate the Wikitext. You have a student who's working on that using XSLT style sheets to go directly from the LaTeX to Wikitext using LaTeX ML. A lot of LaTeX ML is a great piece of software, and it has, in fact, there's already been the use of this to generate Microsoft Word output from LaTeX. That was a project that a student was working on this summer. So this is a viable thing, and we're working on it. Ultimately, one of the most crucial aspects of this is generating a search engine so someone can search the mathematics. And this is something that Moritz is working on his PhD on, one aspect of his PhD thesis. Now, for the DLMF, there's a wonderful search engine which allows you to do search. So one of the options is to port the DLMF search engine to MediaWiki, and that's something we're thinking about, or taking advantage of other search engines which are already out there, as long as we give it the appropriate semantic information so we can, succeed in doing this. The other aspect is the output of formula data. We've incorporated these right-clickable menus using MathJax, and what we'd like to do is output the kind of information that users would like to have in order to process that formula. So, for instance, you'd like expanded LaTeX, so the users can put it in the paper. Semantic LaTeX, which takes advantage of the macros for people who want to build LaTeX with semantic information built into it. And then we'd like to output presentation MathML, which contains the information about how the mathematics is rendered, and then content MathML, which contains semantic information, critical semantic information, which you really need to know in order to output something to a computer such as Mathematica, a computer program such as Mathematica, Maple, or Sage. So you really need that. We would like that so someone could just output the formula and Mathematica could then input it. So that's something we're developing at the moment. So just as a sort of a summary of what we actually have, the computer resources that we are currently using to do all this development work. Of course, we have the machines here at NIST, but we also have these external machines. Really, it's not viable for us to put a MediaWiki implementation at NIST. NIST has severe, strict requirements on security, and MediaWiki is a very giant piece of PHP code, which would need to be software reviewed before we could put it on NIST on a NIST computer, which is not viable. It's too big, and also it's always changing. So instead, we've made the choice to host the DRMF externally and all its resources. The XSEDE project, which is currently maintaining 4 instances that we're using. 2 are demo and deployment instances. They work very well. We used it to demo the DRMF at the CICM meeting in Portugal, which I mentioned earlier, and a deployment instance as well, which is something which gives us more state-of-the-art as to where we have been going with the development. We haven't done that yet because our deployment instance is not really up to date because of some issues on the query server. There's no Labs Vagrant installed at the moment, which would be fairly easy to do, I think, which would allow us to because we really want to set things up in an environment that we can just do the install using, for instance, Puppet, which will then do the full install with all our parameters set properly, all the extensions implemented as we go. It's just you essentially type one command and it does the full install. And we really want to do that because we don't want to have to type everything up every time we do everything. So we are using the Wikimedia Foundation to do that since they already have that implemented there. But I'd like to go back to these other XSEDE instances that we are actually actively using. There's the 2 Ubuntu instances, which we're using as servers. There's a LaTeX ML server that we've have running now, and also a Mathoid server. The LaTeX ML server, I've mentioned to you LaTeX ML. If you have basically through the MediaWiki math extension, LaTeX ML is processed. The LaTeX is processed with the macros, and you generate MathML, which is then viewed. And Mathoid displays scalable vector graphics for formulas. I think Moritz will correct me if I'm wrong about that. At the Wikimedia Foundation, we have several instances which are done in conjunction with the MediaWiki math extension, because we really believe that the type of mathematics, these tools that we're developing are very much in line with the goals of the MediaWiki math extension. So they're connected in literally. And then we have development instances that our students are using to do the actual development that we need for the DRMF, which is really nice because, for instance, at NIST, a student could never be given root permission. In fact, even just visitors, you almost never give out root access. I don't have root access to the machines here. But to do development for MediaWiki, you really do need root access. There's no way around it. So we take advantage of the Wikimedia Foundation to do that, to help them develop. And we use GitHub and so forth to maintain our development. And ultimately, we want to upload our developments when they get to sort of a closing stage to a deployment instance, which we actually have there. In fact, I can just show you on the Wikimedia Foundation. This is our Wikimedia Foundation deployment instance at the moment. And it tells you, for instance, what the goals are of the project, and also a link to the Zeta and related functions data that we've actually generated the Wikitext for, and also some formula pages which have proofs in them so you can see how the functionality works. Now, I'd just like to summarize now and close just with some comments about what we're doing and who's doing it. Moritz is actually leading our development team. He's been a great addition to our team and has taken us in directions that we really have wanted to go, and is giving us really the capability to implement these the development. So we're so lucky to have him on board. We've had a series of high school students who have worked since December of last year from local high schools who have helped us with implementing math jacks for menu customization. And Alex Danoff was a student who helped us with the seeding effort and the macro replacement effort. Amber Liu followed up on Jake's work for the menus, and Cherry has really been leading our macro replacement, which is a very challenging problem. Also, Alex worked on some work for extracting mathematical data from the text, which is a very serious and difficult problem, which you could easily have a PhD thesis on. It's very, you could use neural networks to do that. It's extremely challenging, but right now we do it manually, but we've written some software to help us. At the moment, there's also Jimmy Lee, who's working with Moritz on doing mathematical search. They've recently submitted some results to the NTicker competition, which is a well-known competition for search engines. And that's actively encouraging, and he's continuing on with us. So is Cherry. She's continuing for her second year, and so is Jimmy's continuing as well. And we also have two other students who are working with us they've committed to the full year. I'd also like to mention Bruce Miller, who, without his work that he's done, we would be nowhere, because he developed the macros themselves over the 10 years that the DLMF was in development. So we rely on him desperately for advice and any input he can give us. Also, he's on the W3C team for MathML and XML, so we're so lucky to have him here. Also, Abdu Youssef, who's a professor in the computer science department at George Washington University, who also developed the DLMF search engine. He's also here on a regular basis now, and he's so interested in and has done research in for quite a bit of time in most of the areas that we've discussed today. So we're lucky to have him here.
Hey, Howard. Nancy had a comment on the chat. Nancy, do you want to follow up on that?
Yeah, thanks, Marlon. I have to take off at the top of the hour, and just in case I didn't get a chance to ask the question, I typed it in the chat.
Oh, sure.
Howard, this was a fantastic presentation. I was really happy to see this. I would be really interested in kind of the tie-in to computational science at the HPC level. I was interested to hear about the ties to Mathematica and MATLAB and things like that. But you could almost see the repository, kind of expanding with people's HPC implementations of some of the different algorithms and kind of how that might play into reproducibility efforts and different discussions like that. I'd be interested to hear your thoughts on something like that.
Well, I mean, when I did my physics PhD thesis, I had to develop an algorithm to compute the gravitational field of a self-gravitating object. And in order to do that, you have to integrate a Green's function. And if you want to take advantage of symmetries of that Green's function, you have to express it in terms of special functions. Special functions just appear all over the place in numerical simulations. So there's really no way around them. And I think for me, I think that's the main tie-in with massively parallel computing, for instance.
I mean, and then there's all the different solvers that people use to approximate, some of the algorithms, and I think that's what it would be kind of interesting because there are so many different ways of going about some things.
Oh, I'm sure, and it's very useful to have all this information would be at one particular instance because most of this stuff is distributed in books. And I know it's taken me my entire career to get familiar with the books which contain all this information. And I know most people are not at that stage. So if we're able to make this stuff accessible and usable, I think the more accessible and usable this information is, the more algorithmic development is going to be able to prosper and increase into new areas.
Can I make one? Can I just say one thing, which is not specifically about? It's more about the digital library, the mathematical functions. There's a lot of information in that on the web, and especially on the website, about available software for special functions. So if people are interested in knowing what libraries are out there, what the capabilities are, you can use the DLMF as a place to find where to go.
Yeah, and in fact, we can really specifically just click on that in the DLMF, click on software. You can see this giant table of various functions, what the software packages are, and you can learn all about them by just going directly to the DLMF. Okay. Thanks for that, Nancy. If you don't make it to the end, it was nice talking with you. I just wanted to finish up on this question of semantic information and how we want to build into it and build from it. Basically, LaTeX ML generates presentation MathML, but what we'd really like is content MathML, which really contains the information about how symbols interact with each other, and also ultimately you would like them to also tie into real-world entities and mathematical definitions for symbols. But the content MathML, which is supposed to contain that semantic information, is not currently, very good. It can be improved. And how do we improve the content MathML? For one, we need to resolve ambiguities associated with certain mathematical notations, such as superscripts or subscripts. You don't know what a superscript mean. Does x to the 0, for instance, mean raising x to some power, or is it like an index for some variable, such as it commonly occurs in general relativity? And then other things such as sums, products, integrals, limits, those contain subscripts and superscripts, but they have very specific meaning, and you would like to tie that information in so you know exactly what it is you're talking about. The content MathML, which is generated by LaTeX ML, doesn't currently have that information in it, and we would like to improve the content MathML, which is generated by LaTeX ML, so that it does contain the semantic information. Other examples are if you have something like f of a plus b or f open parentheses a plus b, does that actually mean some symbol f multiplied by a plus b, or is it some function f evaluated at a plus b? So we would like to develop macros which would specifically tell you that information, and a computer could then interpret this data in a precise way. Also, primes, is some sort of naming for a variable, or does it mean a derivative? Again, we would like to develop macros which contain that information and develop the content dictionaries with links to these macros with these mathematical definitions. So for some object, we know exactly what it is we have. And then generate phrase books which will allow you to go between different syntaxes, like, for instance, a Mathematica syntax or a MATLAB syntax to a LaTeX syntax with the macros. So it's just as an example, if you had LaTeX source, you wanted to generate Mathematica source and go from Wikitext, then you would want to build these kind of phrase books, and this is the research that we're doing while maintaining the content MathML. I think that's a good place to stop. I really appreciate you guys listening, and also all the help that XSEDE has been in getting us going. When we had a server that we were using to display it, and we lost it right before we had to present at the CICM meeting in Portugal, and XSEDE jumped in, got everything working. Marie Ma and Mike Lowe really helped us get everything going so we could actually have a demo at CICM, and we really wouldn't have been able to do that demonstration if it wasn't for you guys. So I would really like to say thank you for all the help you've been.
My question was always, where's the people who have time
Hey, somebody needs to mute.
a job? I don't think
Somebody needs to mute.
That's not us.
Yeah. Thanks a lot, Howard.
Sure, no problem.
Yeah, I'll go ahead and close out if you have anything else.
No, that was it. I could finish up. Ask Moritz if there's anything he'd like to add. No, he says everything's okay. So if there are any questions, I'd be happy to answer them.
If we have any questions, just go ahead and speak up. I'll also say, while people are digesting, that we have a regular XSEDE conference every summer, so you missed the one that was in Atlanta a couple of weeks back. There's another one coming up next summer. I don't know the exact dates, but it'll probably be in July, and that'll be in St. Louis. And so we welcome you to submit a little paper or abstract for that as well.
Oh, great. Yeah, sure, we will.
Any questions from anyone?
Hi, this is Sudhakar from NCSA.
Oh, great.
Is there a way to represent this in code, like Fortran or C, or in some kind of an abstract code, parallel or serial?
I think that's even more ambitious than generating Mathematica. I mean, Mathematica code is code, but if you want to do some numerical computation in relation to these formulas, there's no hope of writing a computer program to do it. People spend their entire careers, many people, to write code to compute special functions. So, yeah, you would have to use some pre-existing library, C library, and I'm sure, as Barry mentioned, there's lots of these things which exist. You'd have to take advantage of those. And then also you'd have to choose some library. So the syntax for evaluating a special function is going to be different depending upon the library you choose. And I think this is extremely ambitious. I don't even know how you would continue from that at the moment. I don't know.
I think you have to distinguish between the presentation of formulas and writing computer code, even in the very sense of the kind of algorithms you would use, depend a lot on stability issues, on what ranges of the parameters you're talking about. It gets pretty complex.
That's non-trivial, definitely. For numerical analysis for computing special functions, it's quite complex. People have had lots of successes, though, and there are some great libraries and algorithms.
We're at the top of the hour. Do we have any last questions? All right, I'll assume not. So thanks a lot, Howard, very much, and we hope we'll continue to provide good service for you.
All right. Thanks. I appreciate it.
Thanks, everybody.
Thanks.
Bye-bye.
Bye.
Bye, everyone.
Are you all still there? No, it stopped.